Okay, so we will start with this chapter 17, pick up where we left off. Tests of significance. Can you remember what another word for that is? Tests of significance, we can also call them hypothesis tests. Right? Hypothesis tests, same thing. So if you hear me say test of significance or hypothesis test, it's the same thing. And we're going to go over the reasoning, why we need them, what we do, how do they connect to confidence intervals, how do we state the hypothesis given a scenario, what is a p-value, p standing for probability value, and what is statistical significance, and then how do we test for the population mean? So how can we test for that? When it says tests for a population mean, it's meaning hypothesis tests. That's what this chapter is all about. Okay, so we want to think about it this way with the picture again, and pictures really help us understand this. So if we have our mean is believed to be 86, I believe this was from an example I used with ice cream. So if the package says 86 grams, then that is what we believe, and we're going to test that value. Instead of constructing a confidence interval where we can just check and see if 86 is within the range or not, instead of doing that, we can run a test of significance. In other words, a hypothesis test. Yeah. Yeah, so what happens is this is our, let's say, our claim. And we claim that it's true. We believe it's true. And then let's suppose we just hypothetically go out and we get a random sample. And we get a random sample, and let's say the mean of that sample is 87.8. It's close to 86. So we probably would continue believing 86 is a good value, right? We would believe it's true because it's close, right? But if we had have calculated the sample mean to be 110 grams, that's getting pretty far from 86, and we're far in terms of the distribution, so we probably would not continue to believe 86 is true, and we would reject that claim. So, and that, in simple terms, is basically the hypothesis test. We're going to test a hypothesized value and see if it's believable or not. Okay, and so we'll go through the steps on how to do that. That's what this chapter is all about. Okay, so confidence intervals, though, are good. They're very connected to this. They're almost they're used hand in hand. When our goal is to estimate a population parameter, i.e., like for example, mean mu. Example mu, the mean. But when our goal is to show the population parameter is equal to some hypothesized value, then we use significant tests or hypothesis tests. And we then test the validity of the claim, right? Is it valid or not valid? Okay, and so we have two hypotheses. We have the null hypothesis, that's this one here, H subscript naught. And it's pronounced, it's spelt, this here is N-A-U-G-H-T, naught. Just comes from mathematics notation. So H subscript naught is mu is equal to 86, let's say. So it's always equal. We always have an equal sign because we claim it is true. It's equal to 86. And then we have an alternative hypothesis. It can be any one of these three cases. It can be does not equals, less than, or greater than. Any of those three cases. And each hypothesis test will just have one alternative hypothesis. right? So that's the null, and the alternative is this one for A, the alternative, H subscript A. How can right, so if you're not sure what you're testing, like in the ice creams, it could be less or greater than, right? So it depends on the context of the test. So we could test it's less than or greater than, but if we're not sure of either of those, we just say does not equal, which means does not equal, stroke through it, means it could be, we're testing for both ways. We're testing greater than or less than. Yeah, does that help? We'll see that more in the pictures too. So the null hypothesis, H naught is mu is equal to some hypothesized value. This here is a value, H, and so we have mu naught, that's a number that you're testing. And it's assumed to be true until proven otherwise. And so the test is designed to assess the strength of the evidence against the null hypothesis. That's going to be the p-value. And the verbal statement for the null hypothesis is no effect or no difference. Okay, so this translates into a statement about the possible values of a parameter. Remember, we're talking about parameters here. Parameter is the population mean. And we will only consider the population mean in this chapter. We could do the population proportion, you could do the population median, you could do the population, any parameter you wish. But for us, we're going to focus on the mean. It's the most common, all right? The alternative hypothesis is a contradiction to the equals. So notice that the null hypothesis, it's always, if you can remember this, it's always equal. So if a question says, what is the null hypothesis? Select the option that is equal. The null hypothesis is a claim that is thought to be true. So it has to be equals. And the alternative hypothesis is the opposite to that in either three ways. So does not equals, less than, or greater than to that hypothesized value. So it describes the situation when the null hypothesis is not true. And it means, in terms of verbal statement, it means some effect is occurring or some difference, right? And so this translates into a statement that contradicts, as I said, the statement made by the null hypothesis. So the alternative hypothesis is the hypothesis the researcher suspects is true. It's the purpose of the test. So we have a claim, and then we're going, well, we think it's not equal to that, and then we go ahead and get our data and test it. The data is the evidence, right? So we base it on that random sample. So we start by assuming that the null hypothesis is true, innocent until proven guilty. Next step, we then take a random sample of observations from the population of interest that claim is regarding, and compute something called the test statistic. Okay, we'll see how we calculate the test statistic. And then we finally, from the test statistic, we decide whether or not the sample data obtained presents sufficient evidence to doubt the null hypothesis. If there is, then we reject the null hypothesis and we accept the alternative. If there's not enough evidence, then we cannot reject, or we do not reject the null hypothesis, right? And we accept it instead. And so it's guilty beyond a reasonable doubt. If not, we say that we do not reject the null hypothesis. It remains innocent. So it's the court of law analogy for this test. That's the basic idea. So here's the three statements. So we have some, so here's the three different cases. You can run the test three different ways. You pick one, and then you go and get your data. So one of these cases will be chosen by the researcher. So it will be H naught, which is mu equals some hypothesized value versus the alternative, which is going to be in the first case, case one is greater than. Case two is, so you can see here, greater than. That's case one. Less than. Or does not equals. If it's greater than or less than, we call that a one-sided test. And it has just one, we're just looking at one end of the tail. We're looking to see if the data falls in that range. Okay, and here as well, we're looking to see if the sample mean falls in there with the test statistic. And three is two-sided, so we look at both greater than or less than. So we're looking at greater than and less than. So we're looking at both ends of the tails to help with our decision. That's a two-sided test. So one-sided test versus a two-sided test. That's three. Notice in this slide that every null hypothesis, case one, case two, or case three, they all have an equal sign, right? It's always an equals. Right? Always equal for the null hypothesis. Equal, equal, equal. Case one, two, and three. Whereas the alternative will never have equals. Alternative is either greater than, less than, or does not equals. So that helps keeps it straight. Right? So if we look at the one-sided test, this is case one. So this is like case one. We have our null hypothesis where mu is equal. We know it has to be because it's the null hypothesis. Mu is equal to some hypothesized value, mean. And that's it right here, the mean. And versus the alternative, which is greater than. So we right away, we have a one-sided test. Okay, one-sided test. Once the researcher calculate or determines the null and alternative hypothesis, they then go and get the data. The data then is calculated. You get a mean and you have your standard deviation, you know your n, you know how many observations you took, and you plug it all into what is called the test statistic. The test statistic is just like a z-score, right? Z equals x bar, subtract mu naught, which is our hypothesized value, divide by sigma, divide by square root n. And know what all those pieces mean. What is x bar in words? X bar is the sample mean. What is sigma? Standard deviation. Which standard deviation? The population or the sample? Population, yes. That's this one right here. That's x bar. We know that mu is the hypothesized value. It's coming from here. And we know n. N is the size of our sample. So know what all the pieces mean? Once you have your test statistic, you will get a number. It's like a z-score. And what are we going to do? We're going to plug that number. That z plugs right into here. This is our test statistic right here. I already wrote it down, test statistic. And because this is a one-sided case, this is case one. If you were to be doing a hypothesis test using case one, you would have the p-value equal to, and p-value is a probability, And we're going to get the p-value equal to the probability that z is greater than z, and we know how to do that because we have been doing that throughout the course, right? We know the area under the curve is equal to the probability. And if it's greater than, we know we have to do 1 subtract the probability, right? Remember, if it's greater than, right? We have to remember to do 1 subtract the probability. Catherine? Yeah, the scenario. So you're given a narrative and then you plug in the values, and the question could say, there's so many pieces to this, right? Step 1 is state the null and alternative hypothesis. You could be asked that. Step 2 is calculate the test statistic, right? So you could be asked just what is the value of the test statistic. Step 3 is then get the p-value. Step 4 is going to be make a decision. We'll see how to do that. And then I always like a step 5. What on earth does this all mean? In just plain, simple language. So we'll see what it all means. All right. Okay, because sometimes we get wrapped up in all this notation and formality. You just want to always remember that first slide here and go, okay, this is what we're doing. We're testing a claim to be true, and we're going to get some data, and we're going to look at the mean. Yeah, of course, we're going to have the population standard deviation and the n and all that. We're going to get a test statistic, but we're looking at the mean, and we're really testing to see how close it is. If you think of that idea, the test statistic, where does the test statistic fall? If it's way out in the tail, then it's not going to be held. We're going to reject it. We're going to reject the 86 as true. And we'll accept the claim that the alternative is it's greater than. Okay, so think of keep an eye on the basic idea of this test, because we can kind of get sideswiped into all these steps. Okay, just remember the goal is to go from the null hypothesis, which we claim, to making a decision. And what does that decision mean? So we could do also the other sided test, which is case 2. This was case 1. Let me just write it out again properly, because this was case 2 from that slide. And you can see we're looking at less than this time. So we have the null hypothesis. Take note, it's the same. It's always equal to some hypothesized value versus the alternative. In this case, I have it in orange, less than. We then make that statement. Researcher then goes out, collects the data, and calculates the test statistic. X bar, subtract mu naught, divide by sigma over square root n. We get a number. That's a number, right? The test statistic, z, is a number. We plug that into our p-value, and we just look we look that up on our table, right? Because the test statistic is really a z-score. It's a z-score from the table. We've standardized it. It's called a test statistic because we're running a hypothesis test. So in terminology, in this context, we call it a test statistic. But just think of it, it's still the same z that we know, that we've learned throughout the course. We plug it in, we get the probability, i.e. the area under the curve. And it turns out if it's less than 5%, we often reject the null hypothesis. Usually we use 5%. So that will help us make the decision. We'll get to that more in a moment. So here's case 3. Case 3, we have the two-sided test. Again, notice the null hypothesis is the same as case 1 and 2. It's mu equals some hypothesized value versus the alternative hypothesis, which is does not equal. So you can see in the picture, pictorially, we're looking at both, right? We're going to calculate the p-value and get that. We calculate the test statistic. I guess I kind of stopped there last time. Let me just grab this. And the test statistic, should know by now, is the same as well. So the test statistic is the same for all 3 cases, 1, 2, and 3. X bar subtract mu naught, divide by sigma over square root n. And then we calculate our probability value, our p value. It's a capital P value. This time we multiply 2 times the probability that z is greater than the absolute value of z. Absolute value, so absolute, these are absolute bars. So if I have like -2 and I remove the bars, it's just going to be 2. So whether the value is positive or negative, when you take the absolute value, right? This is from our mathematics toolbox. If you take the absolute value, you get 2. So if the value is +2, you would still take 2, right? Because it's absolute. Just a reminder of what those bars mean. So if you get a negative test statistic and you plug it in here, you need to keep always the positive. When you remove the bars, you'll keep the positive. So let's say it's -2.13, then you'll plug in +2.13 and then multiply it by 2, and it will give you the area under the curve for greater than Z and for less than Z. Yeah. Yeah, it just, when you take the positive and you multiply it by 2, because of the symmetry of the distribution, it works for us. It's handy. What we're doing is we're really checking to see if Z is less than some value or Z is greater than some value, right? It's really looking at both sides. But doing the shortcut, where this is the formula 2, this is a 2 times, that's multiplied, like a star, the probability that Z is greater than some absolute value of Z, the absolute value. Here it is here, pictorial summary. These are the 3 cases. So case 1, this was case 1, one-sided, case 2, one-sided, and case 3 was the 3-sided. So again, the researcher will only do one. They'll just pick one that they want to know about. And it really depends on the scenario. Depends on the context of the problem, whether you go greater than, less than, or does not equals. If a researcher's not sure about case 1 or 2, then the default is always does not equals. Okay. So what is this p-value all about? It's going to be the value that helps us make a decision on the test. Reject or do not reject. That's our decision. And so we assume that the null hypothesis is true, right? And the probability that the observed outcome would take a value as extreme or more extreme in the tails, it would take a value as extreme or more extreme than that actually observed is called the p-value of the test. So that's the formal definition. It's the probability that the observed outcome would take a value as extreme or more extreme than actually observed. And we always assume that the null hypothesis is true. That's the formal definition of a p-value. In short, it measures the strength of the evidence. It's what we, if you want to put it in short terms, it measures the strength of the evidence against the null hypothesis. So the smaller the p-value, the stronger the evidence, right? There is against the null hypothesis, because that means it's not likely. So if the p-value, if the probability is really, really small, then that means the probability is really, really unlikely that the null hypothesis is true. And we stop believing that it's true and we say we reject. Okay, so small p-value equals stronger evidence, to reject. Okay, it just, small p-value means small probability, right? If you have a small probability, then the chances are low that the null hypothesis is true and you reject, if you think of it that way. So the probability that the observed outcome would take a value as extreme or more extreme than actually observed is the p-value. So we make a decision based on some predetermined alpha. This alpha, we look at it like this, alpha. And alpha is usually equal to 5%, usually. So we make a decision by comparing the p-value to some predetermined alpha. Alpha is the level of significance. That's called our level of significance, alpha. And it's sort of like a ribbon there. It's a Greek letter, A. And if the p-value is as small or smaller than alpha, then we reject the null hypothesis and say that the data is statistically significant at the alpha level. So if the p-value is less than or equal to alpha, then we reject the null hypothesis. And we say that the data is statistically significant at the alpha level. So it means that we have a statistically significant result because we've rejected the null hypothesis. Okay. So this is what happens. Or if the p-value is greater than alpha, then what do you think? What's your decision? If it's less than or equal to alpha, then we reject the null hypothesis. But if it's greater than alpha, what would you do? We can't reject, right? Yeah, we can't reject. Then we do not reject, right? Then we cannot reject. Whoops. I jumped ahead here. What happened? There we go. We cannot reject the null hypothesis. There, squeeze it in, right? And then if we cannot reject the null hypothesis, then the test is not statistically significant at the alpha level, okay? So we'll do lots of examples to see how we do this. Step 1, state the null and alternative hypothesis. Step 2, get the data and calculate your test statistic. Step 3, get the p-value and then compare the p-value to alpha. Step 4, make a decision. Reject. There's only 2 outcomes, reject or do not reject. Okay. And then my step 5 is, what does it mean in the context of the problem? Okay. Right, so statistical significance. It means the sample, that's the data that you went out to collect to get that test statistic, it showed an effect larger than would occur just by chance. Okay, so it means it wasn't just a fluke, it means that there was strong evidence to reject the null hypothesis. Right? If it just happened by chance, it would be just random, but it's saying that statistical significance means that we do have something here, we do have an effect, and the sample shows that the effect is larger than what occurred just by chance. This in R squared. R squared is the correlation squared, and it's in the context of regression analysis to assess the fit of the data. This is a test of significance where we're testing some hypothesized value for a parameter in the population. So it's quite different than R squared. Pardon? No, it's they're kind of unrelated depending on the context of what you're testing. They're kind of unrelated though. Yeah. So keep R squared in the regression toolbox for this course. It's related to chapter 5. And then this is just the p-value for the test of significance. No relation to the correlation. Yeah, no relation at all. Right, because what we're doing is we're just getting a sample and calculating that test statistic, getting the p-value, make a decision, and then put it in words into the context of the problem. Here it is here. Here's our summary. Step 1, state the null and alternative hypothesis. Check. 2, collect the data and calculate the test statistic. 3, calculate the p-value. And then step 4, compare the p-value with the level of significance alpha and make a decision. So here's how we make the decision. If the p-value is less than or equivalent to alpha, we reject the null hypothesis and accept the alternative hypothesis. That means the test is statistically significant. Right? It was sort of the suspicion of why the test took place in the first place. And then it's like, yes, our suspicion was right? So that's case 1. Or the second outcome could be if the p-value is greater than alpha, we do not reject the null hypothesis, and we can even conclude the test is not significant. The test is not statistically significant in this case. So there's only 2 ways, right? The test, like there's only one of 2 ways that you will conclude this test, right? The test is either statistically significant or it's not. If it is statistically significant, it means you rejected the null hypothesis based on the p-value and the alpha comparison. Otherwise, you did not reject the null hypothesis. It was not. This is a really good slide to put it together, right? 4 steps. Again, I'm going to add a step 5 based, sort of like saying in words, what does this mean? Based on the scenario. So we'll look at an example. Yep. We reject if the p-value is less than or equal to alpha. And so when we do that, we reject the null hypothesis and accept, because the null hypothesis and the alternative are opposites, right? The null is always equal to some hypothesized value. And that is what's up for, that is what is being claimed, and that's what's up for the test. And so we make a decision based on that p-value. Okay? We compare it to the alpha, and then we reject it or not. So let's try with insurance claims. Let's try an example. So let's say the insurance company is reviewing its current policy rates. When they set their rates originally, they believe the average claim amount was $1,800. Okay, so that's how they base their premiums on, is based on their average claims and the data from that. So that's their hypothesized value. Average claim is 1,800. They are concerned that the true average claim is actually higher. Perhaps it's gone up than what they had based their premiums on. And because of that, they could potentially be losing money. So they need to run a test to see if it actually has. How do they do it? They, instead of going through all the claims, they take a random sample of 40 claims and calculate the average as 1,950. Okay, so you can stop right there, 1,950, and you go, geez, that is higher than 1,800. Maybe we should just stop the analysis right there and tell the insurance company, yes, they should just raise the premiums because the average was 1,950 and it's way higher than 1,800. But it needs to take into consideration, we could just stop there. We're suspicious that it's probably gone higher, but we want to run a formal test to see if there's statistical significance by getting the test statistic, including the standard deviation, which is $500, and the size of the sample. Take into consideration the size of the sample, which is 40. And then it makes it more formal, more scientific than just comparing the average 1950 to 1800. So we'll run the test to see if we'll use a 5% level of significance, and we'll test to see if the insurance company should be concerned. So what are the null and alternative hypotheses based on this scenario? Anybody? Yeah, Lee? It is, yes. That's the null hypothesis. So it's going to be H naught, H subscript naught, colon, it's always colon because we don't have the equals in here yet. It's going to be mu equals some hypothesized value, and they believed it was $1,800. So we'll do it like that. We'll put the dollar sign in, 1,800 versus the alternative, which is going to be what? So notice I put equals because it's always the null hypothesis, that first claim is always, always, always equal to some value. That's the value that the insurance company has based their premiums on. They believed, it says right here, they set their rates. They believed that the average claim amount was $1,800. So what is the alternative in this case? What would we test? Greater. Right, because they think then maybe it's higher. Here's a key word here. I'll highlight it. Higher. So that sort of tells us that we want to go higher. Mu is greater than 1,800. So we have here a one-sided test. Okay, it's a one-sided test, and that's part A. So that could be one question. Could be asked. Let's go on to part B. What is the value of the test statistic? So they have calculated a random sample. So the value of the test statistic will be Z equals X bar subtract mu naught divided by sigma over square root m. That's our formula. And we're going to plug in, what is X bar? Yes. Yeah, the 40 claims. And so X bar is the average from those 40 claims. Yeah, so it's the sample, right? So X bar is the sample mean, and it will be 1,950. So 1,950. And notice I'm subtracting 1,800 because that's mu naught. This is mu naught right here. Mu naught is 1,800. We're going to divide that by sigma. Sigma is 500. There it is. That's the population, sigma. So that's going to be 500. Divide by the square root of, we said 40 claims. And that should give us a value. That should give us, anybody have a number? 1.8974. Well, how about 1.90? We'll round to 1.90 because the table goes up to 2 decimal places. So is that okay? Do that one. And so because it's greater than, we then plug that into here. So the p-value equals the probability that Z is, what am I going to put here? Less than, greater than, multiply by 2. Which formula do I use, right? We have which case here? Okay, right. So greater than. It's greater than. And how do we know it's greater than? Is because we look at the alternative hypothesis. And that's how we know it's greater than there, then it's going to be greater than here. So the p-value is based on the direction of the alternative hypothesis. We just plug that value in. So it's going to be 1.90 because that's our Z. And then we know how to do this from before. It's 1 subtract the probability that Z is less than 1.90. We get the table and we subtract that. Sorry about that. 1 subtract. So we'll look up 1.9. Let's see if we can find 1.9 in here. This row right here, 1.90. So 1.90, I get 0.9713. Everyone agree with that? 0.9713 for 1.9. We go back to our that ends up equaling 0.0287, which is 2.87%. So now we need to remember how we make a decision. We are going to compare, right? Compare the p-value and alpha, which is 0.05. That's the 5. It comes from here. Use 5% significance level. That's alpha. And we're going to compare them. So we ask ourselves, is the p-value less than or equal to alpha? That's the question we want to know. Is the p-value less than or equal to alpha? So you go, well, it's 2.87% and alpha is 5%. What's the answer? Yeah, it's yes. So we say yes. So the p-value is 0.0287 is less than 0.05, right? That was our decision right there, right? Our p-value is 0.0287 and it's less than or equal to 0.05, our level of significance. And we say yes, then what do? If the answer to that question is yes, do we reject or we cannot reject? Do not reject. Or do we reject? Reject. Okay, some of us aren't sure, so let's go back because it's brand new to us. Let's go back and consult our summary. So this is a really good slide. You want to know this slide. If the p-value, so here we're at step 4, if the p-value is less than or equal to alpha, we reject. So are we less than or equal to alpha? We said yes, so we have to follow this slide, then we reject. If it was greater than alpha, then we would be cannot reject. Okay, so know this slide really well and you can make that decision. So we reject H naught mu is equal to $1,800. Okay, so in the context of the problem, the insurance company that would run this test, and they do, but they run these all the time, they would go, okay, it's not $1,800. We've rejected that. That means we have to go back to the drawing board to set our rates because it's higher. Because if you're rejecting this, then that means you're accepting, and I'll put it in orange, we accept HA mu is greater than 1,800. Now, we don't know how much greater, so further investigation needs to be done by the insurance company, but we have enough evidence right here to go, we need to make an investigation. We need to look back at this and set our rates based on a higher amount than 1,800, right? Because if they're setting their rates based on the average claim as being 1,800 and the average, there's evidence now that the average claim is higher than that, which we just showed, then they need to go back to the drawing board and re-investigate what they should set it at, right? So that's our first hypothesis test. That's how it's done. It's done for a variety of different domains, lots of different examples. You'll see the textbook, there's lots of different examples as well that show you how we use these. Let's try another one, paint coverage. So we have a manufacturer, well, this is an industry question, sort of like our ice creams from our last chapter. So let's say they advertise 1 gallon of paint will cover 400 square feet of an interior wall. Now that's what's being advertised, right? 1 gallon gives you 400 square feet, or does it? So some local painters suspect that the average coverage is considerably less and decide to conduct an experiment to find out. That's basically what these are. These tests are like an experiment. You can do or get a simple random sample. They did an SRS of just 5 cans of paint, and they calculate the average coverage to be 380 square feet, right, from that sample. Assume the paint coverage is normally distributed with the standard deviation. Let's say the standard deviation is roughly 20 square feet. And we'll use a 5% level of significance. That's our alpha right there, 5%. And we'll test to see if the local painter suspicions are correct. So let's see, what do we have? What is our null and alternative hypothesis? What are we testing? What's the claim? The long-held belief. The null hypothesis, yes. Pardon? 400, yes. So mu equals, right? It's always equals, good. Always equals 400 versus, what should we do here? Based on the wording of the problem, they suspect the average coverage is considerably less. So we'll go with less, right? This is the key word here, less. So they figure that the average is less. So we'll go U mu is less than 400. So it's always equal to some hypothesized value and the same number. Make sure the same number goes here. It doesn't change. Don't change the story. You want to keep it. It's equal to 400 and then it contradicts that 400 by either, all you're changing is the sign here. The mu and the 400 stays. You're just changing the equal sign to less than, greater than, or does not equals. Based on this example, it's less. So we're going to test if it's less than 400 square feet because they think the gallon's covering less square footage. Part B, what is the value of the test statistic? So let's get that. So we know that the test statistic is Z, X bar, subtract mu naught divided by sigma over square root n. Let's grab all those pieces. What do you think X bar is? Now that in words is our sample mean. So what would you put in for X bar? 380. Let's put it in. Yes, 380, sub that in. 380, subtract 400, divided by standard deviation was given at 20 square feet. And what was the size of our sample? 5 cans of paint. That was our size. So just 5. And we get that into our calculator. Anybody have a number? What is the value? This could be a question too. Any step here could be a question. So what's the value of the test statistic? No one from the back? Side? The front? Anybody have a number? Yes? 2 point. It's going to be negative 2.24. So we actually don't take the absolute value in this case because this is case 2. So we get our p-value next. Our p-value is the probability that Z is less than or greater than. What do we use? Yes? Yeah, less than. I'm just going to grab this orange again because this really highlights less than is the alternative. Just take a look at the alternative. It's going to be less than here as well. And it's going to be negative 2.24. So there's no absolute value in this case. It's only case 3 when you're doing the two-sided test. So we have a one-sided test again. Let's write that down. This was a one-sided test. And so we're going to just get that value. Just get the table, right? Just use the table, negative 2.24. Okay, where is negative 2.24, right? How does that look? Negative 2.24, I get 0.0125. 0.0125. That's 1.25%. All right, 1.25%. We need to make a decision. We can ask ourselves again, is the p-value less than or equal to alpha? And remember, alpha is 5%. So basically we're checking, is the p-value, which is equal to 0.0125, is it less than or equal to alpha, which is equal to 0.05? That's basically what we're asking. Is this number less than this number? Yes or no? Yeah, right? We have another yes. we have another yes. The answer is yes. So this is yes. And so therefore we are going to, we reject the null hypothesis that the gallon covers 400 square feet. Now, if you recall the ice cream example from the confidence interval chapter 16 we did last week, we calculated a confidence interval for the true weight of the ice creams. A 95% interval was 84.1 to 86.1 grams. This was our interval. And because it was 95%, if we use alpha at 5%, those two add up to 100%. So if the test is a two-sided test, the hypothesis test is a two-sided test, we can use this method, right? So the null hypothesis, so we want to check and see if the null hypothesis mu is equal to 86 grams. Sort of how we started this chapter too with the first plot, right? The first picture we looked at versus the alternative hypothesis, which was does not equals 86 grams. And we see that 86 is in the confidence interval, so the company can relax and be rest assured that their packaging is correct. They can continue. They don't need further investigation because it worked out quite well. So that's what this bullet says here. Since 86 is within the confidence interval, we do not reject the null hypothesis. That's the conclusion of the test, and it is not statistically significant. Right? So it's quite quick. If you have a confidence interval and it goes with a two-sided hypothesis test, you can check for any value. What if it was 84? If the hypothesis value was 84 grams, then you would reject because it's outside. It's a little bit less, right? It's outside. What if you were testing 80 grams? Then you would reject as well, right? Because it's outside, right? So you can see how these tests work. And so you can use in summary, you can use a two-sided confidence interval to conduct a hypothesis test, basically, simple terms, provided the hypothesis test is two-sided and we have the alpha at 5% and it all adds up. So if you had a 90% confidence interval, then alpha would be at 10%, okay? To make it all add up to 100. So let's say we have a certain population. This is the last slide. We have a certain population normally distributed with unknown mean and standard deviation equal to 1.2. So a 95% confidence interval for the true mean is 1.1 to 2.8. So this would be 1.1 subtract 0.8 is going to be 0.3 to the maximum would be 1.9. Right? Because it's in the form of estimate plus or minus margin of error, I just unraveled that to give me my minimum value to my maximum value. So the full range is 0.3 to 1.9. So we can test the hypothesis is equal to 1.2. We'll do one for 1.1 and 0. So let's do for the null hypothesis is equal to 1.2 versus the alternative is it is not equal to 1.2, right? And this is going to be a 95. So these have to be alpha equals what? Alpha must equal, if the confidence level is 95%, so the alpha has to equal, 5%. 5%. So what would you conclude? We can jump. We don't need to calculate a test statistic. We don't need to get a p-value. We don't need to do that. We can jump straight to the conclusion using that confidence interval. So what would you say? Yeah. Accept it. Yes, accept the null hypothesis. So another way of saying that is we cannot reject H naught, which is equal to 1.2, since 1.2 is within 0.3 and 1.9. Make sense? Let's do number 2. Mu is equal to 1.1 versus it is not equal to 1.1. And we'll keep the same alpha because this is based on the same confidence interval, which is 95%. And so what would we say in this case? Reject or cannot reject? We're testing 1.1 and we're comparing it to the confidence interval. So we'll do the same thing like we did number 1, but it's a different number. Instead of 1.2, like number 1 was, it's 1.1. So, yep. It is, so we cannot reject, right? We cannot, same conclusion. Right? It's the same conclusion that was cannot. Mu equals 1.1 since 1.1 is within 0.3 and 1.9 and 1.9. All right. Now we're going to check 0. So this time the null hypothesis is equal to 0 versus it is not equal to 0. Not equals. Alpha is 5%. What do we say? What's our conclusion of our test if we were to test this using the confidence interval? 0. Is it in or out? Out. Good. So we conclude what are we going to do? Correct. We reject the null hypothesis that mu equals 0 since 0 is not within 0.3 and 1.9. And the test result in this case 3, when we're testing 0, would be considered statistically significant at the 5% level. Researcher, that's the process. You have your null and alternative hypothesis, and then you collect your data. Okay? So we'll do step 1. What are we going to say that it's equal to? 9.5, right? That's the belief. And remember, these things change. If you go and get if you've ever had any blood work done, if you've had a surgery or even just a regular routine blood work, they have in the results the range of what is quote normal, meaning healthy. That's sort of what normal means, healthy and you're safe. And I always, when I get mine checked, I always check and see Am I in that range? Right? I want to know, so I'm checking my value, right? And these things change. So cholesterol level, these things change over time. They start to realize that, blood pressure too, you have a top number and a bottom number, 120 over 80, and those safe levels will change and say, well, we're okay if it goes down to 60 and so forth. Or cholesterol levels will change based on more data, more research, and they'll change criteria of what's healthy. So the standard here is 9.5. I'll leave the units off, but it's milligrams per deciliter versus HA, which is going to be mu does not equal. What should I put here? 9.5. Yes, good. Thank you. It's always the same number, 9.5. Don't change and put in any sample mean. Don't put anything from the sample in, because you have to remember this step 1, there's no data yet, right? These claims all go in when they do their ethics proposals or they state their claims before any data, right? The whole proposal of how their research will be conducted and that before any data is collected. So just remember that. Don't be putting in anything that is provided to you from the data, because it's assumed not to be known yet. So now we have the data and we can get the test statistic, which is going to be Z equals X bar. Subtract mu naught over sigma over square root n. What is X bar? So what's the average? The average calcium level from the sample. Now we want the sample, because the data now has been collected. We're past step 1. We've collected some data. What did they get? It's right there. Yep. 9.57. Correct. So 9.57. It was right here. Right. So you can go, a clinic measures the blood calcium level of 180 healthy pregnant women. So this is the sample right here. Right? It's not every woman that's pregnant. It's only 180, right? So it's a sample. And then we get 9.57 from their average for calcium level, and then subtract 9.5, divide by standard deviation was here. That's sigma, 0.4, divide by the square root of n. What was n again? 180, yes, 180 women. And we get, so we calculate this, 9.57, subtract 9.5, divide by 0.4, divide by the square root of 180 women. Does anybody have a value for this? No? I have something, I can redo mine. Does anybody have a different value? Yeah. 2.35. I get 2.35 as well. So just check your answers, 2.35. All right. We're going to then do our step 3, calculate the p-value, which is 2 times the, this is where the absolute value, we don't really need it though, because we already have a positive, Z. So that's going to equal, and this is, by the way, a star. That means multiply. So 2 times the probability that Z is greater than 2.35. I didn't really need the bars because it was positive. So I need to go 2 times, and this is going to be 1, subtract the probability that Z is less than 2.35, right? Make sure that all stays together. Because it's greater than, I have to do that trick that we know so well. 2 times, we're going to grab the table and go 1, subtract that table value, get the table. So we'll go and we'll get the table. That's 2.35. $2.35 right there. 2.35, right? 2.35 for our test statistic. I get 0.9906. That's going to be 2 times 1, subtract 0.9906 is 0.0094, and multiply that by 2 is 0.0188, or 1.88%. We multiply it by 100. So it takes a few more steps because it's two-sided, right? We're looking at greater than or less than. And then we go, okay, now we need to make a decision. Is the p-value less than or equal to alpha? And we're going to use alpha at 5%. I'll put down here, use alpha equals 0.05 or 5%. That's the standard for these tests. So we'll go 0.0, which equals 0.0188 less than 0.05. Right? Is the p-value, which is 0.0188, is it less than 0.05? Is it less than 5%? The answer is yes. Yes. Therefore, what are we going to do? Our decision is to reject. So this is important, right? This is important. We have statistical significance. We have statistical significance because if this was done in a lab and they did collect the data from these patients and they come to a conclusion like this, then the long, quote, healthy value of 9.5 has been rejected. And this is what happens. They don't do it just on one test. They'll do more tests and more studies over time, and they will reach a conclusion. And you'll see that quite often these values will change of what's healthy. This is how it's done. The only way it can be done is through these formal tests.